pretty much everything that you need to know about neutrino mass constraints. There is a Colab notebook, and I would like to invite you to open it now and to execute the first cell which installs the Python packages, because it takes a long time. So you could start it up and start it downloading and then ignore it. And then by the time we get to actually using it, it will be complete. So I will do that for you, just to demonstrate. Yeah, whatever. Okay, and now hopefully it will just sit there doing its thing. Okay. Everybody done that? I'm going to say that's a yes. Okay, so what is a neutrino? So a neutrino is a neutral particle with a very small but non-zero mass. It interacts via the weak force and not via, for example, the electromagnetic force or the strong force. It is the last standard model particle whose mass is not known. And it is ubiquitous, and there is a huge solar neutrino flux of the Earth, which is about 6 × 10⁻⁻⁻ neutrinos per centimeter squared per second. Because it is a small, almost massless neutral particle, there are no good images of it. So this is my attempt at making a beautiful image. It's just a nu in a circle. It's the best thing I can come up with. Why are they massive, right? It's tempting to say, okay, we have a very small particle. Why is it not just another massless particle? Why not just like a photon? We have detected neutrino oscillations. So you know the solar neutrino flux, or what the solar neutrino flux of the Earth should be, because you know the reaction rate in the sun's core. And you can measure the actual electron neutrino flux at the Earth using Kamiokande or using SNOLAB. And this is about 1/2 to 1/3, depending on energy, of the expected flux. And the solution to this problem is that some of the electron neutrinos flip into muons or taus, and the fact that they flip shows that they are massive, okay? Because they experience some passage of time. So neutrinos are known to have a mass. It's just known to be very small. There are limits on the mass. So the lower limit is less than 0.056 eV from neutrino oscillations. The upper mass is set by this particle physics experiment called Catrin. And there is an upper limit, a very recent upper limit on the electron neutrino mass of 0.45 eV. Since there are 3 active neutrinos, this means the total neutrino mass is less than about 1.4 eV. So I would like you to look at the image here, which is Catrin being installed. And you will notice that the Catrin is about as large as it can be without needing some small German town to be demolished, right? So we don't want to demolish German towns, willy-nilly. So it's difficult to make Catrin 10 times bigger, right? Something 10 times bigger would have a great deal of trouble being installed, okay? So, obviously we cannot possibly solve this problem. So the only way to do it is to do cosmology. The forecasts for a better technique, not a bigger experiment, but a better technique, are that you could perhaps someday constrain the electron neutrino mass to less than 0.04 eV and the total mass to like 0.12 eV. My point here is to say that there's a gap between 0.056 and 0.12 that even a reasonably futuristic, better experiment has difficulty closing, right? So this is a thing which is not known and which is reasonably difficult to do from a particle physics perspective. So you would have observed that this is a cosmology school. So your next question is, what does this have to do with cosmology? Well, I'm glad you asked that question. So during Big Bang nucleosynthesis, you produce neutrinos freely. At high energies, you have this weak interaction, which is in equilibrium with, in equilibrium and happens constantly, where a proton and electron will decay to a neutron and a neutrino back and forth. And the ultimate result of this is the production of a cosmic neutrino background, which is kind of like the cosmic microwave background in that it is decoupled. It decouples at the point when the weak interaction rate drops below the Hubble rate, which is a time much earlier than the microwave background decouples. In particular, it's before the annihilation of electron positrons, and so it has a somewhat lower temperature than the CMB does, because the CMB has been heated by electron positron annihilation. these neutrinos exist everywhere, right? This is a ubiquitous neutrino background, just like there is a ubiquitous photon background. These are very low energy neutrinos, right? So although we can detect the neutrinos from the sun, we cannot detect the neutrinos from the neutrino background because they are substantially lower energy. So, however, because we cannot detect them, I can't produce a map of the actual neutrino background, but I can produce a simulation of the neutrino background, shown here. And I hope that you all agree that it is tremendously beautiful. So this is a redshift 0 simulated map with overdensities shown in white and underdensities shown in sort of dark blue. And the dots here are galaxies. So you'll see that there's kind of a big overdensity of neutrinos here. They don't quite line up with the galaxies for reasons, but they kind of somewhat trace the large scale structure. You might, if you've seen a CMB map before, you might want to look at this and say, oh yes, these anisotropies are encoding information about the primordial universe, right? They decoupled very early on. Maybe if we could look at this, we could see what the modes were doing when they decoupled. This is unfortunately not the case, right? So because neutrinos are massive and they are affected by gravity, they are perturbed quite significantly as they come across the universe for us. So really these anisotropies you're seeing is the effect of the gravitational potential between neutrino decoupling and today. There's still cosmological information there, but it's not like the CMB, right? It's not like a snapshot of the matter density at the time of decoupling. I want to say unfortunately, but we can't observe it anyway, right? So it doesn't really matter that much. So the problem with this is we cannot detect these background neutrinos, right? So still we want to do something with it. The thing we want to do with it is we want to measure what the neutrino mass is. How do we do that without detecting it? Well, so there's two effects, right? So the first effect is that the neutrinos change the background evolution of the universe just a little bit. So they decouple about a temperature of 1 MeV, which is when the universe was about 10 to the 10 Kelvin. Because their rest mass is extremely small, when they decouple, they're initially ultra-relativistic. So they redshift like 8 to the minus 4, just like radiation does. At later times, because their momentum redshifts and their mass does not, they will eventually become non-relativistic. And once they are non-relativistic, they will redshift like 8 to the minus 3, like matter. So you have this species which is redshifting one way at early times and another way at late times. And by looking for when this transition happens and measuring the expansion rate during this transition, you can start to have a handle on what the neutrino mass is. As an aside, so I want to make it clear that Tom did not do the thing that I'm complaining about in his lectures, which is a great reflection on how excellent Tom is in many ways. Okay, so this is not a dig at Tom. So you might have seen in textbooks, people make statements like, oh, matter is pressureless and radiation has a pressure like P is, the pressure is the density divided by 3, right? And then there's the fluid equation here. And there's a derivation of this fluid equation from the first law of thermodynamics. You say, well, energy is conserved, therefore something with this energy density will redshift like this. Something with this energy density will redshift like this. Matter has no pressure, therefore it redshifts like 8 to the minus 3, right? Who's seen this? You've all seen this, right? I do not like this framing, okay? So look, this is really, we're doing this because we don't want in intro cosmology courses to do general relativity at you, right? But this is really coming from the covariant conservation of the energy momentum tensor, which is that T mu nu derivative is 0, which is, of course, so this is kind of true because the relativistic generalization of energy conservation is this, right? But it's not exactly true, right? Because what we're really doing here is we're saying, okay, so the total energy in a frame co-moving with the background matter so that the momentum is 0 for cold dark matter is something like this. The momentum redshifts like 1 over A. And then when we work out this equation, it turns out that something where the momentum is 0 or the momentum is very small redshifts like 8 to the minus 3, whereas something where the momentum is much, much greater than the mass redshifts like 10⁻⁴, right? So this is not really, this statement that matter is pressureless and radiation has a pressure. This is not really quite what's going on, right? Like this pressure in the Friedmann equations is not really a pressure. This is just a reflection of the fact that if you do the relativity equations, you get something that looks a bit like a pressure, okay? So with this aside, it should now make sense to you why neutrinos redshift like 10⁻⁴ initially and like matter like 10⁻³ at the end, right? So initially, they have P much, much greater than M, and they redshift like 10⁻⁴. The momentum will drop off, and eventually they redshift like 10⁻³ because M is greater than P. In the middle, they're going to kind of smoothly interpolate between these two regimes, right? So this is what's going on, right? So there will be a transition where the momentum and the mass are roughly equivalent, and this happens at about redshift of 2000 for a 1 MeV neutrino. And more precisely, we can smoothly interpolate between the two regimes, and we can do the equation, and we can plug it into a numerical solver like class or like CAM, and it will tell us what the background evolution is. Okay? By the way, I apologize that all my slides are just words and equations. Normally, I would try and put a picture in, but none of the pictures really relate to what I'm talking about, right? Because neutrinos do not, you can't make pictures of the neutrinos, right? Like this is a problem that I've always had. So normally, if I'm giving a talk to a colloquium or whatever, I would put little pictures there so people feel engaged. But I was like, this is a school. Like you're students, so like I can make you suffer, right? So I'm just going to give you the equations and the text. Okay. So this is the Friedmann constraint, and this is the expansion rate. So this is the expansion rate as a function of the matter density, the radiation density, and the lambda, the cosmological constant density, and then there's this extra neutrino term here, right? So the way that we're measuring the neutrino mass with the background is that we can measure this expansion rate at a bunch of different redshifts, using the BAO, using the CMB, using a whole bunch of things. And then if we change this term, the expansion rate will change, right? And so the CMB and the BAO peaks will move in a measurable way. This sounds, I hope that does this sound completely plausible to you? Yeah? Right. As long as you know what omega matter is and what omega radiation is and what omega lambda is, right? So if you know these three things, then changing the neutrino mass will change the expansion rate, right? But there is some kind of degeneracy going on if you don't know all these things exactly. So in particular, if you were to take this nice clean omega lambda and make it vary with redshift because I don't know, dark energy is dynamical, then your neutrino mass constraints suddenly become a lot weaker, right? So implicitly, sometimes people will write these models and they'll say, okay, we have this neutrino mass constraint, assuming that there is a cosmological constant, right? Because you have one extension to the lambda CDM model at a time, and assuming that dark matter is cold and non-interacting, right? So a lot of the neutrino mass constraints you see in the literature have this kind of implicit assumption built into it. Let me, so as an example, and this is an example, I think this is one of the best abstracts for a paper I've read in a long time, right? So this, there's a DESI paper on the neutrino mass, which is based mostly on measuring the background evolution, measuring the BAO peak. And in the abstract, they say, assuming the cosmological lambda CDM model, which is this thing I just wrote down here, we report a neutrino mass less than 0.053 eV, breaching the lower limit from neutrino oscillations. So, oh no, right? Like we showed in particle physics that it was bigger than 0.056, and now cosmology is finding this less than 0.056. Like what's going on? This is a calamity, right? Like we've measured the neutrino mass and it's different in different parts of the universe. Oh no, what could be happening? So fortunately, we used the clever trick of continuing to read the abstract. And at the end of the abstract, it says, but the preference of DESI and CMB data for an evolving dark energy model offers one possible solution. In the W0 WA CDM model, where dark energy is evolving, we find mu less than 0.163 eV resolving the neutrino tension, right? So this is an example. If you were to assume that dark energy was a cosmological constant and dark matter was a cold, non-interacting dark matter species, then your bound that you get from on the neutrino mass from measuring the BAO would be wrong, because your BAO data prefers this dynamical dark energy model, right? So the right thing to do, the Bayesian thing to do, is to have all of them in the chains at once and to place constraints while varying all parameters, which is what DESI does, okay? So you might be wondering what the point of this is. Well, okay, so the point of this is to say nice things about DESI. The other point of this is to make the point that measuring the neutrino mass from cosmology is doable, but it is extremely difficult, even conceptually, because you have to find something that you have to find you can't just take your favorite cosmological data and throw it into your chain and say, hey, here's a neutrino mass constraint, right? You have to be willing to assert that you have the other components of the universe, the matter and the lambda, reasonably under control in order for your constraint to be valid. Okay, so as an aside, this is a bit weird, right? This equation, it seems kind of unnecessarily complicated, right? Why do we need two terms here? We have a matter term and we have a neutrino term. Why do we need two of them? When we already have these neutrinos, they are, can we just combine them? Can we just say, okay, the dark matter is neutrinos. Let's just forget about this dark matter thing. We know neutrinos exist, right? So can these things be dark matter? So points in their favor, they are known to exist. That's a good plus point. They are weakly interacting massive particles, which is to say they're massive and they interact with a weak force. In addition, their production at Big Bang nuclear synthesis tells you how many neutrinos there are. So you can increase omega nu by increasing the mass of the neutrino. So this sounds reasonable, right? Why not just dial up the neutrino mass until it has the right level of omega nu that it matches omega matter, right? Why not just make the whole universe neutrinos? Alas, this doesn't work, right? So why doesn't this work? So dark matter is cold, neutrinos are hot, right? When neutrinos are formed, they're formed ultra-relativistically. They still have a significant thermal velocity, and that makes it difficult for them to form galaxies, right? The whole deal with dark matter is that it's cold. It is much colder than the baryons. It collapses into these potential wells. The potential wells need to be there, or you cannot have the gas forming galaxies within them, right? So if the universe went neutrinos, and I did once run a simulation. I was hoping to, come to a talk like this and make a movie with a simulation of a neutrino-based universe and the structure formation that happens in it. I do not show this movie because it is incredibly boring. Literally nothing happens, right? There is no structure formation. It is like one frame, smooth universe, still smooth universe, okay? Nothing happens. But because I have tormented you with so many slides without any movies in, this idea has actually reached Hollywood, right? So Hollywood knows that neutrinos are hot dark matter, and so they made, if I turn it on, hang on. Okay. Do I need the audio? I might need the audio on. I was going to just put the microphone next to my laptop speaker, but no, it will work. If I do this. Yeah, so this idea has reached Hollywood. Hollywood knows that neutrinos are hot dark matter. And in this movie 2012,
looks like the neutrinos coming from the sun have mutated into a new kind of nuclear particle. They're heating up the Earth's core. They suddenly act like microwaves.
So there we go. They're hot dark matter. They mutated and they're heating up the Earth's core. I found this on YouTube, and the comment says, this is not. I do not own this movie because it's so bad. this is just a parody copy because it's too bad for me to own it. I was like, okay, fair enough. So the neutrinos are hot dark matter. They do not heat up the Earth's core. They do not interact, but they also do not form galaxies. Oh no!
Looks like the neutrino.
How do I get to the next slide? Here we go. Okay. So we can work out how much of the dark matter they are, right? So they are a small component of the dark matter, right? They behave like matter, they redshift like matter in the late day universe, and they have some total contribution to the mass density of the universe. This is the formula for it. It is the sum of the three neutrino masses divided by 93.14 h squared. You can say 100 h squared. That's roughly 0.5% of the total budget of the universe for the neutrino mass of about 0.2 eV, right? So for relevant neutrino masses, these are a small component of the dark matter. They're not a zero component of the dark matter, but they're a small component of the dark matter. We can also compute, rigorously what I told you kind of in words a little moment ago, which is that they have some thermal free streaming length. So you can work out what their momentum is. You can work out their average velocity, which is their average momentum divided by their mass. It is their temperature divided by the neutrino mass divided by the scale factor, with some extra factors of the Boltzmann constant in there that I'm just going to pretend aren't there for now. And this comes out to about 150 kilometers per second with the normal redshift scaling and with 1 eV neutrinos. So 1 eV neutrino will have an average velocity of 150 kilometers per second, which is a bit less than the virial velocity of the Milky Way. 0.1 eV neutrinos will have a velocity of 1,500 kilometers per second, which is substantially larger than the virial velocity of the Milky Way, right? So what this means is that neutrinos are not clustering within any halo with a virial velocity less than their average velocity, right? So the Milky Way generally will not capture neutrinos. Like generally, any structure that is somewhat larger than the Milky Way will not capture neutrinos. You have to go to a cluster scale to imagine that neutrinos are captured by the halo. They are free streaming out of any halo and out of any small scale structure. But wait, I was complaining about how difficult it is to measure the neutrino mass from the background evolution. But wait, this has given us a new clue, right? These are things that are not clustering on small scales. They're not clustering on scales smaller than the distance traveled by a neutrino moving at this velocity in a Hubble time, right? They can't because they just free stream out of any structure. So this gives us a new measurement for the neutrino mass, which is that because they are a small component of the dark matter not clustering, there will be less clustering than you would expect if all the dark matter were cold dark matter, right? So more rigorously, this is the free streaming scale. This is the average velocity of the neutrino divided by the Hubble time. And this comes out to be about 8 megaparsecs for a 1 eV neutrino at redshift 0. And what this is going to do is going to mean you're going to have a small component, 0.5% of the matter density. So like, maybe 5 to 10% of the dark matter that is not clustering. Right? And that is going to suppress the growth of structures. So you're trying to build a Milky Way, you're trying to build a galaxy cluster, and some part of the dark matter doesn't want to fall into the potential well, it just wants to go straight out. So this is the thing that we can measure, right? This is the stronger information that comes on neutrino mass from cosmology. Oh man, I just gave away the, okay, well, pretend I didn't say that. So there are these two techniques. One is to detect the changes in the background evolution. The other one is to detect the suppression of structure between the free streaming length. Which is the larger one? Who thinks it's the first one? Who thinks it's the second one? My goodness. You're being funny. Right, it's the second one. The second one is more powerful, right? So why is the second one more powerful? It's more powerful because it's an integrated effect, right? So the changes in the background evolution happen just about once. The suppression of the structure growth changes the growth rate at each redshift, right? So it changes the growth rate at redshift 10, structure grows a little bit, it changes the growth rate at redshift 2. Because it is a change in the rate, when you integrate it, the effect is much larger. So in particular, it turns out that the suppression of structure is about 8 times the fraction of neutrinos in the fraction of the dark matter that is neutrinos. This is the ratio of the suppression of the power spectrum divided by the power spectrum. This is the omega neutrino, this is omega matter, and the prefactor is about -8. This is a result from linear perturbation theory, and this is really setting the depth of this slope here, right? So this gray band is the scales measured by DESI. I would like to ask you, where is the best place to look for the effect of neutrinos on the growth of structure according to this plot, right? Where should we be looking? Not where the gray is. Any suggestions? This way, this way? This way, right? Yeah, right. So the big signal is here, right? This is where we should look, right? There is a big suppression on these small scales. So, okay, so this is great. The only slight problem is that linear perturbation theory stops working, about here, right? About here, the overdensities become larger than unity, and we can't do perturbation theory anymore. So all of this wonderful cosmological information over here is going to remain unused. Except some people know how to run simulations. So because I like running simulations, in my mind, this is a feature, right? This is an excuse to run simulations. Like other people who really care about neutrinos and cosmological parameters, they might say this is a bad thing because it makes life more difficult. But for me, it's a great thing because it makes life more difficult. It means I have an excuse to run simulations. It keeps me busy. There are multiple probes of these nonlinear regimes. So the top one is CMB or weak lensing. Another one is the Lyman alpha forest, which is what I'm going to talk about in tomorrow's talk. You can also measure the clustering of galaxies, the number counts of galaxies, and the number counts of clusters. So the clustering of galaxies is separate from the number counts of galaxy clusters and the Soniev-Saldovich power spectrum. So all of these are sensitive basically to the amount of power on some scale, which kind of varies between about here and about here. And they're usually like point measurements, right? They'll measure a single scale to some accuracy. Yeah, let us now pause and go to the notebook. And hopefully, in the last half hour, all of you have successfully done this, right? And install Classy and everything is working for you. So the next thing to do is to execute this cell, and who can do that and successfully not get an error indicating the Classy installed correctly? Cool. Can anyone not do that? Great. Okay, so in order that you have a sense of ownership, what I've done here is I have left some parameters blank. So here I've set up a class set of parameters for no neutrinos and massive neutrinos. Here are some basic parameters, basic accuracy parameters. Here is a cosmology. There's nothing special about this cosmology, except in the second half of the talk, we're going to have a simulation. And this happens to be the cosmology that I ran this simulation at, right? So this is the reason for these parameters. I set the parameters, and then here, I will set the neutrino parameters. So I want you to set up a second cosmology with massive neutrinos, assume all 3 neutrinos have the same mass of simplicity, and make the total neutrino mass 0.4 eV. The class neutrino mass parameter needs to be a comma-separated list as a string. So, okay, so this parameter, NNCDM, is the number of massive neutrinos. Who would like to guess what it's going to be? 3. That was a good guess. Yes, well done. Was that a question? What's the question? Can I zoom in? Yes. I can zoom in. How do I zoom in? Like that? Does that work reasonably well? Can you see better at the back now? Great. Okay, so 3. Okay, so there are 3 massive neutrino species. We need a comma-separated list of the 3 neutrino species. Anyone want to guess what it's going to be? You can raise your hand. So we want all of them to have the same mass for simplicity, and the total neutrino mass to be 0.4 eV. This is testing your ability to divide by 3. Yes, who said that? I don't remember, but you did. Okay, 0.13333. Oops. 0.13333, 0.13333. Yes, you see, I am a challenging lecturer who sets difficult exercises. So now let's set this, this final parameter. So this thing is NUR, or the number density of ultra-relativistic neutrinos. Here, for the massless case, I've set it to 3.044. What should I set it to here? 0.044. Anyone agree with? Yes, I think it's 0.044. As a side, does anyone know why the effective number of neutrinos is 3.044 and not 3? Right? Like why does it make sense to have? Well, okay, you know, yeah, okay.
One was 0.
So this one should be 0.
0.
Oh yes, I'm sorry. Thank you. Yes, that would have been that would have made quite a different power spectrum. We would have noticed that. Anyone know why it's 0.044, 3.044 relativistic neutrinos rather than 3? Right. You answered the question already. Anyone else? I'll come back to him if no one else answers. All right, go on. Tell me the answer. Right. So they're slightly coupled during electron-positron annihilation, right? So there are 3 neutrinos. This is an effective number of neutrino species, right? So what this is that really what this is saying is that the omega value for the relativistic neutrinos is a little bit larger than you would expect it to be, because they're still a little bit coupled during electron-positron annihilation, right? So it's really, it would be more sensible if the parameter we all use in our chains was like omega ultra-relativistic neutrino rather than n effective neutrino. But that ship has long ago sailed, and there's nothing we can do about it. So we have to deal with this 0.044. Okay, so that should work. And now we can plot it. Okay, I'm ready to, everyone ready to execute this guy? Let's do it. At this point, I got bored with, redacting so in principle, this should work now. At this point, I got bored with redacting the notebook, and so it's just execute the cells, right? So you can follow along by executing the cells yourself. So this should show a reduction. Oh no, it didn't. Oh, uh-oh. There we go. Hooray, okay. All right, so this is going to show a suppression of structure, just like I showed in the plot over here. This should show a suppression of structure due to neutrino mass. So what I'm doing is I'm evaluating the linear theory power spectrum for some k at redshift 0, and with neutrinos some k at redshift 0. I'm sure this isn't the best way to use class, but it's the way that I figured out in 10 seconds of looking at the class manual. You can see that there is a suppression, right? So you see this kind of smooth suppression. So why is it a smooth suppression rather than a step function, right? It's because the free streaming length changes with redshift, right? So the suppression here is neutrinos, is the free streaming length when neutrinos just became non-relativistic. Then this is the free streaming length at some later redshift. And then after the free streaming length has dropped, neutrinos on this scale starts to cluster. Then the free stream length drops a bit more, neutrinos start clustering on a larger scale, and so on and so forth. And then this here is roughly the free streaming length of redshift 0, right? So that's why it's a kind of smoothly varying curve. Okay? I also computed sigma 8 for you. So this is 0.4 eV, remember? And I had class show you that sigma 8 went from 0.85 to 0.77, right? So this is actually a fairly big effect, right? So, you know, this is something that, that you could put constraints on. And it makes sense, right? Sigma 8 is the fluctuations measured on 8 megaparsec scales. That's around about here. Okay? So now we can do it at other redshifts. Does anyone want to guess what it's going to look like at other redshifts? Is the suppression going to be larger at higher redshift or smaller at higher redshift? All right, so who says the suppression will be larger at redshift 2 than at redshift 0? Who says it will be smaller? Yes, you are all correct. Well done. Hooray. Okay, so this is the neutrino suppression as a function of redshift, right? So I've done it at redshift 0, redshift 1, and redshift 2, and at redshift 9. And you can see that it gets smaller at higher redshifts. Why is that? That is because this is an effect on the growth factor, right? I told you it's an integrated effect. At higher redshifts, there has been less time for the integration to take place. I have 3 minutes left. So, okay, so that is the linear theory suppression to neutrinos. Next time, I'm going to talk about how to, after the 10-minute break, I'm going to talk about how to simulate structure formation with neutrinos. Yeah, I'll see you after the 10-minute break. Thank you very much for listening.
Let's have 10-minute break.